This lesson is about solving nonlinear systems of equations. When we work with two nonlinear equations, for example, an equation of a circle, an ellipse, a parabola or hyperbola, we may expect different number of roots. It's not like just in solving linear systems of equations that we may have either no solution when the two equations really represent two parallel lines, or one solution when the lines cross each other in one spot, or infinitely many solutions when the two lines are actually one and the same line. When solving systems of nonlinear equations, we may have different situations. We may have different number of roots, not just 0, 1, or infinitely many, but, well, let's see. Our two equations may represent a line and a circle, and even in this situation we may have three different outcomes. We may have no solution, 0 solutions, or one solution, as in this situation when the line is just touching, it is tangent to a circle, so we end up with one solution. Or we may have a situation that the line crosses the circle and gives us exactly two solutions. But we may have different shapes, for example, a circle and an ellipse. They can cross each other, like on this diagram, creating three possible solutions, or maybe like on that diagram, we may have up to 4 possible solutions. So here we could have 3 solutions or 4 solutions. And here's another example of a circle and a parabola that crosses the circle in 4 places, so we may have 4 solutions. Could we actually have infinitely many solutions like in the case of system of linear equations? Of course, yes, because the two equations may represent, for example, one and the same circle. So if the second equation represents exactly the same shape, we will end up with infinitely many solutions. But generally, a system of nonlinear equations may produce more possibilities, may produce 0, 1, 2, 3, 4, or infinitely many solutions. Obviously, the examples that I show you here, they do not exhaust all the possibilities, but it seems like 4 solutions is the most that we can obtain when solving a system of equations that involve any of those conics that we talked about. How do we solve systems of nonlinear equations? Well, basically nearly the same as systems of linear equations. We can use either the substitution method or the elimination method, or both of them if needed. Here we have the first example. We need to solve this system of equations. It's a good idea to realize what each equation actually stands for. What kind of curve does it describe? So the first one represents a circle with center 0, 0 and with radius 5. Okay, so we have this situation, we have some sort of circle, and the second one is a linear equation. So the number of solutions will really depend if this line touches the circle or going across or not touches at all. Let's see. Think for a second, which method would you use in this situation? Well, here it's very easy to solve the second equation for one of the variable, for example, for y. So I have y equals x plus 1, and then I can use this expression in the first equation. So I can replace y by x plus 1. So let's see what the first equation will give us. X squared plus, and instead of y we have x plus 1 square equals 25. Oh, that's great. Now we have a single equation with one variable, so we know how to solve it. Let's perform perfect square here. So we end up with x squared plus, remember to use 3 terms when you square binomial. So we have x squared plus double the product 2x plus 1 equals 25. Collect like terms, we have 2x squared plus 2x. And now we can move the 25 to the left, so it's 1 minus 25, so it's negative 24 equals 0. At that point, I would divide the whole equation by 2 because all the coefficients are even. So we end up with x squared plus x minus 12. And that's something that we can actually factor. So let's factor this. Two brackets with x's. The product is 12, the difference 1. So 4 and 3 should work. Since the difference is positive, so the 4 will be positive and the 3 negative. Okay, that's great. So we already know what the x should be. From this bracket, x is negative 4, or from that bracket, x is 3. However, when solving system of equations, we need to end up with an ordered pair of numbers. Each x is the input for the y, so we need to find the corresponding y that matches this x, and that would satisfy both of these equations. Therefore, we could actually use any of those equations, whichever is easier. And looks like the easier one is the second one, because it's linear. So now we can take the x value and go back, plug in to the substitution equation. Therefore, the corresponding y for x negative 4 is negative 4 plus 1, leaving us with negative 3. That tells us that x negative 4 has a corresponding y negative 3. So it's first part of our answer. We can already start answering our question. The solution set to this system of equations contains a ordered pair of numbers negative 4 and negative 3. But that's not the end. We also need to figure out what if x is 3. So if x is 3, then the corresponding y is, and again plug in the 3 to the substitution equation, we have 3 plus 1 equals 4. So if x is negative 4, then y is negative 3. If x is 3, then y is 4. Okay, we can list this in our set of answers for the whole problem. The other point that satisfies the two equations is 3, 4. So, since we know that there are actually 2 points when the two curves intersect, we know that this situation really looks somehow like this. We have 2 solutions. The line is crossing the circle. So that was the algebraic way of solving it, but it's a good idea to see it geometrically, so we can graph both shapes. We have a circle with radius 5, and we have a line, x plus 1 comes through the point 1. That's our line x plus 1. And as you see, we have these 2 solutions. So it's good to visualize this and confirm if we didn't make any mistakes when calculating. So negative 4, negative 3, oh, looks like it's perfectly fine. Confirms. And 3, 4, that's our 3, that's 4. Yes, these 2 points are our solutions. Okay, in the next example, we deal with 2 equations again. And the first equation is, you figure out what is it. That's a circle with center 0, 0 and radius 3. And the second equation represents, how do you think? What does this represent? Oh, that's a hyperbola because we have a minus here. So hyperbola. And it is a square hyperbola because both radii along the x and y axis are actually 3. Okay, let's try to solve this algebraically. Think for a second which method would be more convenient to use in this situation. Well, I think it would be easier to use elimination method. Why? Just because I see plus y squared and minus y squared. When I add side by side my 2 equations, the y squared will be eliminated and result in the equation in one variable. 2x squared equals 18. And then we solve for x, so x squared is 9. Therefore, x by itself is either 3 or negative 3. 2 possibilities. Those 2 possibilities may create 2 or may even create 4 points. Let's see. Again, we can plug in those x values to any of those equations. So for example, I can choose the first one. And instead of x, I'm using 3 or negative 3. So the first time, instead of x, I plug it in 3, and when squared, it becomes 9, and then I solve for y. Since I have 9 on this side and 9 on that side, the y squared is actually equal to 0, which means that y by itself is equal to 0. So this way, I produce already the first answer. The input is 3, and the corresponding output is 0. Now see if the second x value will produce different answer. Maybe you can already guess. Well, -3 when squared, it will become 9 as before. So it doesn't look like it will produce anything new. It's still the same y equals 0. Y squared equals 0, so y equals 0. So this point doesn't produce different y value, but we have overall different point because the input is different. So the second point is -3 and 0, and that's the overall solution. There's 2 points. So how this may look like graphically? The first equation is a circle with radius 3, and the second equation describes a hyperbola that has 2 asymptotes. Those asymptotes are coming through the points 3, 3 and 3, -3 and the origin. So those asymptotes, they really look like this, diagonals, 2 diagonals. And the hyperbola is shaped by these 2 asymptotes with vertices at -3 and at 3. So we can see that those are the 2 solutions. The hyperbola is barely touching the circle. And one more example. What do we have here? Well, the first line describes a circle because it's x squared plus y squared. Circle with radius, which is the square root of that number, radius equal to 2. The second equation represents a parabola, a well-known parabola. So we have a circle and parabola. Well, you can imagine that this may produce 0 solutions or 1 solution or 2 or 3 or 4 solutions. Let's see what will happen. First, as usual, figure out what kind of strategy would we use to solve this algebraically. I would suggest substitution again because y is solved already in terms of x. So let's plug in this expression to the first equation. We have x squared plus, our y is x squared minus 2, we need to square it, equals to 4. Okay, this time it looks like we will end up with 4th degree equation, but hopefully it won't be too difficult. Let's see. X squared plus square of the first term, x to the 4, minus double the product of the 2 terms, 4x squared, and finally plus last term square, which is 4. Oh, that's good, because on the other side we also have 4, so we could actually cancel these 2 4's. This makes it easier. Let's clean up a little bit. We have x to the 4 minus 3x squared, and it's equal to 0. So even though this is 4th degree polynomial, it's not too difficult after all. We could factor x squared, and we end up with x squared times x squared minus 3 equals 0. The second bracket can be considered as difference of squares. So we could factor it as x minus root 3 and x plus root 3. And this x squared will produce 1, 0. So what kind of roots we have? X equals to 0 from the first factor, x equals root 3 from the second bracket, or x equals negative root 3 from the third bracket. So we have 3 possible entries. They will most likely produce 3 overall solutions to the given system of equations. Okay, for each x, let's calculate the corresponding y using the second equation. So here, if x is 0, our y will be 0 squared minus 2, which is negative 2. Over there, when x is root 3, our y would be root 3 squared minus 2. So it's like 3 minus 2, it is equal to 1. And finally, this x will produce y equals negative root 3, that needs to be squared, and then minus 2, again we end up with the same tree because negative square is positive, so we have 3 minus 2, so it's 1. Okay, we have 3 points, 3 ordered pairs of numbers, and we can list them to create the answer. The answer is the set of ordered pairs 0, negative 2, root 3, 1, and negative root 3, 1. Okay, to see it geometrically, we have a circle with radius 2 and center 0, 0. And this is a parabola that was dropped 2 down, so the vertex is at negative 2. This parabola is just touching the circle at the point 0, negative 2. So that's first part of the solution. And the other two solutions are positioned symmetrically. So this is your x-coordinate root 3, and that one is negative root 3. The value is 1. So the diagram confirms our solutions, the 3 points. In summary, what should we remember when solving a system of equations, either linear or nonlinear? Well, the solution is a set of ordered pairs, so if you find x, you shouldn't stop, you should find the corresponding y. And sometimes the corresponding y is just one number. In some other occasions, you may find that the corresponding y will produce two possible values. Also, when solving systems of nonlinear equations, you may use any of the algebraic methods, either elimination or substitution. It depends on the equations that you have and what seems to be easier.